Okay, sorry for the late. Okay, because there are a delivery come to my house, so I need to settle with the delivery person. Okay. Okay, we continue on the second topic. Okay, on the infinite slope. Okay, where we discuss on the how to determine the factor safety. Okay, on the infinite slope structure. Okay. Okay, so this is just we recap again. Okay, on the previous discussion. Okay. So civil engineer often are expected to make calculation to check the safety of the natural slope, slope of excavation and compact embankment. Okay, this check involve determining the shear stress developed along the most likely rupture surface and comparing it with the shear strength of the soil. Okay, where the shear stress is related to the driving force, while for the shear strength is related to the resisting force. Okay. So this process is called as a slope stability analysis. The most likely rupture surface is the critical surface that has the minimum factor of safety. Okay. So this is how, we need to run for several analysis or several calculation to determine the minimum factor safety number and the optimum location of the what we call it of the rupture surface area. Yes. So this is what we have discussed previously. Okay. Actually this is new, new, similar to this one. Okay. Okay. So the factor safety for the transitional strip is defined as, okay, FR is the resistance, FD is the driving. Okay. So nu W cos theta over W sin theta, okay, or equal to tangent phi over tangent theta. Okay. So this sorry. Okay, this explanation we may find after on the next slide. Okay, so this is the first general explanations. Okay. Clearly, when the dipping angle theta is smaller than the angle of friction phi, the resisting force Fr is greater than the driving force Fd, and the factor safety 1 and the factor safety the factor 1 and the factor safety is greater than 1. Okay, and vice versa. Okay, when factor safety is greater than 1, it is safe. Factor safety is equal to 1 is onset of failure or critical condition, and the factor safety is less than 1, it is fail. Okay. So the task of the engineer charged with the analyzing slope stability is to determine the factor safety. Okay. Generally, the factor safety is defined as tau F over tau D. Okay, the average soil strength, which is the tau F, is equal to C plus sigma prime tangent phi prime. Okay. Okay, this is based on the effective stress concept. Okay, and the average shear strength TD developed along the potential failure surface, okay, also can be used by using the same more column approach by having a D, okay. However, we may use a different approach later on, okay. So this is just to relate by using the more column, okay, approach. We also can have the shear stress of the tau D. Okay. So this is the shear strength, but this is the shear stress. Okay. So the factor safety is the ratio between the tau F and also the tau D. Okay. So for example, we have a ratio between the FC, okay, which is the C prime over CD, C prime D. Okay, for this approach, FC and FV, we may discuss later on. Okay, on the linear failure plane approach, okay, on the finite slide, finite slope. Okay, so this is the, but I just want to introduce, okay, because the first introduction for this part is a general introduction. So it can be used either for the failure plane, for the infinite slope, for the circular type of finite slope. Okay. While for the Fp is equal to tangent phi over tangent phi d. Okay. So Fs, if the Fs is equal to Fc and also equal to Fp, so when Fs is equal to 1, the slope is in a state of impending failure. Okay, generally a value of 1.5 for the fact safety with respect to the strength is acceptable for the design of the stable slope. Okay, so we cannot use 1, but we need to refer to 1.5 for the fact safety value. Okay. Okay. So we may discuss later on the FC and FE. Okay. So on the linear methods, okay, linear methods under the linear failure plane. Okay. So for the linear methods, okay, there will be two types of analysis that we will use. Okay. For the first one is the linear method, and the second one is the non-linear methods. Okay. So for the linear method, okay, relatively simple. Okay. So for the infinite slope analysis, we may use the linear methods. Okay. So there are no non-linear method or circular type of analysis for the infinite slope. Okay. So there will be a linear failure plane, okay, for the finite slope. Okay. So for this finite slope, okay, we may use the FC and FV, okay, in to determine the factor safety, okay, because we need to use the try and error approach, okay. Means that we cannot get what we call as directly factor safety value, okay. So we need to do at least 3 attempts, okay, to get the failure safe to get the factor safety value based on the linear failure plane approach. Okay, so analysis for the case of phi equal to 0. Okay, so there will be another approach by using the linear methods. Okay, so the last one is the wedge failure analysis. Okay, however, I will not discuss in this methods. So then we have a non-linear method of slices necessary for irregular slope geometry, non-uniform soil condition and seepage in soil. Okay, so that is non-linear methods. Okay. So for the non-linear method, we have a method of slices, and also we have a total stress method, okay, whereby it depends on the whereby they use, both of them use the concept of moment, okay, to obtain the factor safety. Okay. So now we discuss on the infinite slope. For the first half discussion, I will explain on the derivation of the equation. Okay, and after that, after we have a break, we discuss on the calculations which is related to the infinite slope. Okay. So slope that extends for a relative long distance and has consistent subsurface profile can be considered as infinite slope. Okay. So I guess I have mentioned previously, okay, where they have a long distance of slope surface. So we can just imagine there are no top and toe, okay, and has a consistent, and then we need to assume, okay, the subsurface profile is consistent with the failures with the surface of the slope. Okay, which is a parallel saw profile with the slope surface. Yeah. Or on the other hand, okay, there are some reference book, okay, where they discuss on the infinite slope, okay, based on this kind of assumption where the failure is happen on the slope surface, okay, similar to this kind of sketch. Okay, failure plane parallel to the slope surface. Okay. So it is different with a linear failure plane, where the linear failure plane, we assume the failure will be like this. Okay. And it is also different with the circular or non-linear method, where the failure will happen like this one. Okay. So, but for the linear, for the infinite slope, so we assume that the failure is parallel to the slope surface. Okay, so this is a common one, but this is some of the researcher or the textbook define for the failure plane parallel to the slope surface, either on the first case on the infinite slope or on the finite slope, okay, can consider as an infinite slope. Okay. Okay. So to derive for the slope factor safety for the infinite slope, okay, so we may assume uh, uh, there are weak layer, okay, present, okay, and then we assume with the length of L. Okay, so this is the weak failure. Okay, so this is the L, while this is the B. Sorry, the height or Z. Some reference book use Z. Okay, so then we need to determine what is the W. Okay, weight of this block. Okay, so by using the same approach with the previous that we have discussed, the previous example that we have discussed. Okay, so the Wn, okay, will be W sine beta, while the Wp is W cos beta. Okay, so later on we need to determine what is the value of the W. Okay, so the W or W is governed from the unit weight time Z or H time L. Okay, so that is the unit weight. Sorry, that is the weight or the W. Okay, where the volume of the soil element times with the unit weights. So here we have L, H, and then we times with the gamma. Okay, so that we from there we get the W. Okay. So the force perpendicular to the plane AB. Okay, so this is the AB. Okay, so perpendicular is the NA. Okay, is equal to W cos beta. Okay, so NA is W cos beta. Okay. Then the W is equal to gamma LH, then times cos beta. So this is the equation for the W, for the NA actually. Okay. Then for the force parallel to the plane AB, okay, which is the TA or the what we call as the driving force, W sine beta or gamma LH sine beta. Okay. Not that this is the force that tend to cause the slip along the plane. Okay. So that is the force. Okay, now we want to get what would be the stress. The effective normal stress and the shear stress at the base of the slope element R. Okay. So then the NA need to divide with the area of the base. Okay. So this is the length. Okay. To get the actual length of of this surface, so we need to divide with the cos of the beta. Okay. So from there, the sigma is equal to gamma h cos square beta. Okay, while for the tau, which is the shear stress, is equal to gamma h cos beta sine beta. Okay. So the reaction to the weight W is an equal and opposite force R. Okay. The normal and tangential component of R with respect to the plane AB are, okay, and R is equal to R cos beta or equal to W cos beta, while TR is equal to R sin beta or equal W sin beta. Okay. So for equilibrium, okay, the resistive shear stress that develop at the base of the element is equal to TR over area of the base. Okay. The resistive shear stress also may be written as okay, TD CD plus sigma tangent TD. Okay, so this is the one that I have told you previously. Okay, where they express the shear stress in the more column equation. Okay, and also they also can express the resisting shear stress by using the equation that we have derived previously. Okay, so we have two equation there. Okay, then from there, okay, they CD, okay, gamma CD, okay, this is sigma, what sigma? Okay, so this sigma, okay, then they put the sigma value in this equation, okay, with the tau, okay, okay, and the tau is based on this equation. Okay. So then they get this kind of equation. Okay. So actually, this what we call as this equation, okay, it is a simplified equation, okay, to be used to obtain the factor safety, okay, for an infinite slope without a seepage. Okay, I will elaborate more later on. Okay, so this is without a water. Okay, for this situation, okay, there are no a seepage or a water or a groundwater, okay, inside the soil surface, okay, or the groundwater is far from the this slope plane, failure plane. Okay, so this is how they derive an equation, okay, to determine the factor safety for an infinite slope where there is no seepage occur. Okay. Okay. So then they include the tau d, okay, in this equation. Okay. Later on, CD over tau h is equal to sine beta cos minus cos square beta tangent phi d. Okay. Cos square beta times tangent beta minus tangent phi d. Okay. So they want to eliminate the phi d in the equation and also the CD in the equation. Then they impose the tangent phi d and also the CD, okay, in this equation. Okay. So then they obtain the factor safety is equal to C prime over gamma h cos square beta tangent beta plus tangent P prime over tangent beta. Okay. So that is the first equation. Okay. we may understand more when we go for some example. Okay, so this is how the derivation that's been made by the author. Okay. Okay. So how to get this one? Okay, first you need to include the CS C prime over FS here. Okay. So if you want to derive this equation, okay, and also the tangent phi d, okay, so you put in here, okay, so you have tangent phi over fs, okay, or you put here, okay, the other one, okay, okay, I have proved it. So we at the end we obtain this kind of vector safety value, okay. So there will be another easy way, but I just want to show some of example, which is if you look on the DAS, Braja and DAS reference book, okay. Actually, I have provided in your e-learning, okay, the notes from the Braja and DAS, okay. So this is how they obtain the vector safety for for a normal slope without seepage, okay. So you just put here without seepage. Then we go for the seepage one, okay. So that is without seepage, okay. Okay. Then they introduce another equation where we can find what is the critical height, okay. Okay, for example, okay, for the granular soil, C is equal to 0, then the factor safety become equal to tangent phi prime over tangent B beta. Okay, so this is the one that we have discussed previously. Okay, this one. Okay, the first. Okay, this one. Okay, so this situation only suitable when phi is equal to 0. Okay, so that's why I told you that we made this. We made this. I will show you how they come up with this tangent phi over tangent. Sorry, when tangent theta. Sorry, when the phi is equal to not the phi is equal to 0. Sorry, when the c is equal to 0. So it is not what we call as a clay material. Okay? Sorry, not p is equal to 0. C is equal to 0. Okay? Okay. So then we get tangent phi over tangent theta. So it means that it rely on the phi value. Okay. Okay. So those fs is independent of the height and the slope is stable as long as beta is less than c. Okay. So is independent of the height and the slope is stable as long as beta is less than c value. Okay. So for if the soil is granular type, okay. So if a soil possesses cohesion and friction, okay, so the depth of the plane along with critical equilibrium occur may be determined as factor safety is equal to 1 and H is equal to HCR. Okay, so this is equation, okay, where we can determine the critical height, okay, where what is the maximum height that can achieve, okay, under factor safety is equal to 1. Okay, so how they derive the equation? Okay, so we may refer to this what we call as this equation and this derivation. So this is tangent. Okay, actually, factor safety is equal to 1, means that the tau f is equal to tau d. Okay, So we need to include the value, sorry, the equation of tau F and also the tau D. And then from there we need to um, rearrange and put the HCR on the left and the rest on the right. Okay. So from there, the equation for the HCR is equal to C over gamma cos square beta tangent beta minus tangent phi. Okay. So that is to determine for the HCR. However, this is for the soil without seepage. Okay. Okay. Now we move to another example. Okay, where they derive an equation for the slope of infinite slope, for the stability of infinite slope, where the stability is having a seepage. Okay, where the slope have a seepage. Okay. So we need to the height of the level of the seepage is at the slope surface. Okay, so that is the height of the seepage. Okay, so we will assume that there is seepage through the soil and the groundwater level coincide with the ground surface. Okay, so this is the limitation of the equation that we will discuss later on. Okay, where we only able to use the equation when the groundwater is coincide with the ground surface. Okay. So the shear strength of the soil is given by, okay, this is the shear strength. Okay, so there from there, the saturated inlet weight of the soil, okay, was used is the saturated inlet weight, where we want to determine the W. Okay, then we put the W, then we obtain the NR equal to saturated unit weight times L times H cos beta. And for the TR, saturated unit weight times L times H times sin beta. Okay. So then the normal stress at the base, okay, actually similar to previous one, but the difference is on the saturated value. Okay. Okay. So the resistive shear stress also could be given by okay, however, for this case, they introduce what we call as the pore water pressure. Okay. Okay, the height of the water in the piezometer placed times with the unit weight of water. Okay. Then from there, okay, we include the new, okay, in the sigma, okay, where the sigma is minus with the new to get the effective. This is the total, while this is the new or the pore water pressure. Then we get the effective stress. Okay, so the new, the sigma. This is sigma, while this is the new or the pore water pressure. Okay, then from there we get the CD plus sigma naught times H cos square beta tangent phi D. Okay. So this is the driving force, while this is the resisting force. Okay. So this is the effective effective unit weight, where saturated minus gamma W. Okay. Normally for the gamma W, okay, either we want to use 9.81 or 9.8, or we can use 10. Okay. 9.81, 9.8 or 10. Okay. So then we rearrange the equation, okay, to get the factor safety. So for this case, okay, this equation only capable to be used if the seepage is on the surface of the slope. Okay, I will show you some of example later on. So this is based on the derivation of the equation only. Okay, so it's very hard to understand unless we can see the example. Okay. Okay, so after this, you need to bring along your calculator. Okay. Because I will show you the example by using this formula and by using another formula. So you need to calculate by using the calculator during our discussion. Okay. Okay, so that is from the dust. Okay, we call it as a dust reference book because I already provided to you the example of the dust. Okay, Braja M dust. Okay, so this is based on Braja M dust example. Okay, where they discuss for the slope without seepage and the slope with a seepage. Okay, so what happened if situation that, okay, for example, if this is a slope, okay, and the groundwater level is located, for example, 2 meter below the slope surface. Okay, while this is the surface failure. So definitely we could not use this formula. Okay, and also the first one. Okay, this one we also cannot use this one because this is without seepage. Okay, and this is the case where the seepage is at the surface of the slope. For this case, the slope is the seepage is 2 meter below the slope. Okay. So in order to solve this kind of problem, okay, so we may look on this approach, okay, where this is from Dr. Noli Gofar. I also provide to you the Dr. Noli Gofar example, okay, where the M approach has been used. Okay, so this is example similar to what has been proposed by Raja M Das. Okay, this one for the fully saturated type of slope. Okay, so similar to this one. Okay, so in order to solve this kind of problem, so we may use the M value. Okay, so what is the M? M is the height, for example, of the water over the total height of the slope. Okay, for example, because Dr. Noli used Z, so ZW over Z. Okay, so means that if this is the failure surface, okay, so for example, if this is equal to 0.8, for example, meter, while this is 1 meter, so the M is equal to 0.8 over 1. So we obtain 0.8 in terms of M value. Okay. Then we may use this M value, okay, to determine the factor safety, okay, based on this kind of problem. So we could not use this approach. Okay, we could not use this one. Okay, okay. So that is for the M. Okay, we may discuss later on. Okay, by looking at an example. Okay, so there is another approach, okay, which is, I guess this is much more easy to understand. Okay. Okay. And it could cater to similar like approach by Dr. Noli, but the this one is not using the M approach. Okay, so this is based on Dr. Noli, sorry. This is based on Dr. Noli where they introduce M. Okay. Okay, so they have M here. Okay. 1 minus M times unit weight. Okay, so this is the tau F. Okay. So to get the factor safety value, sorry. So tau F should divide with the tau M. Okay. So this is the equation of the sigma. So sigma we put here, and also this is nu. So nu include here, while this is for the tau M. Okay. We calculate first for the sigma, nu, and get the TF, and then we determine the TM, and then we obtain the factor safety. Okay. So this is based on Dr. Noli approach. Okay. While this is then we can do a simplification. Okay. The same with the one that does show. Okay. But the idea is we need to understand the basic of this formula. Okay. So for me, it is better for us to use this basic formula rather than we use this simplified method. Okay. So for this case, it's only able to solve the problem if the groundwater level at the surface. Okay. So but by using this kind of approach, we can solve any type of problems because we understand the basic of the formula. Okay, I will show in the example later on. Okay. Okay, later on, so this is for the slope for the critical, what we call for the critical height. Okay, so for example, if to get the factor safety, to get the ZCR for the fully saturated type of soil, okay, so then we can use this formula to determine the ZCR. Okay, this is for the fully saturated. By the previous one that we have discussed is for the unsaturated. Oh, sorry, for the where the groundwater level is far from the failure surface. Yeah. So this is for the without seepage. Okay. But this is for the seepage at the ground surface. Okay. Okay. To understand more, we may look on some of example. I will explain in detail later on, so then you can understand the full discussion on the infinite slope. Okay. So can we have a break for 10 minutes before we continue for the last lecture for today? Okay.